we have made it again, guys. Alright, we're continuing section 5.3 now. In the last video, we ended up talking about rational functions, what a rational function is, and how you sketch and analyze the graph of a function, rational function in the form y equals k over x minus b. Now, I'd hoped that we'd be able to squeeze in the y equals ax plus b over cx plus d equations there. We didn't, so that's fine. We're going to go ahead and get them in this edition of Mr. Klinkerman's videos. And so, let's go ahead and get straight to that. Rational functions where you have a linear function divided by a linear function. The last of what IB needs you to know in terms of rational functions. Alright, let's get through all the things that we've accomplished already. And let's talk about rational functions that are in the form y equals ax plus b over cx plus d. Now, these are not just translations of the reciprocal functions from the previous section. These are kind of brand new to us. So, we're going to have to approach them a little bit differently, but they do have similarities. First of all, the graph of a linear function divided by a linear function is still going to be a hyperbola. And since it's the same shaped graph, it's going to end up having the same basic properties as everything else that we've looked at, in terms of there will be a vertical asymptote, there will be a horizontal asymptote, one of each, whenever we're trying to graph an ax plus b over cx plus d rational function. So we need to talk about what you do to figure out what the vertical and horizontal asymptotes are. Let's start with the vertical asymptote. That's the easiest one. From the standpoint of explaining why it is what it is at any rate. Now, just like with our reciprocal functions and their translations, we can't let the denominator be equal to 0. So that quantity cx plus d there, not allowed to be equal to 0. And any value of x that would make cx plus d equal to 0 would be a vertical asymptote, because it would be a restriction on our domain. So we can find out what the vertical asymptote is by setting the denominator equal to 0. And if we set cx plus d equal to 0, and then we subtract d from both sides and then divide by c, we'll find that the vertical asymptote exists here at x equals the opposite of d over c. Now, I don't expect you necessarily to memorize that ratio, although that works for you. But if you'll remember to set the denominator equal to 0, you'll always find out where the vertical asymptote is. Pretty simple thing to do. Alright, now the horizontal asymptote is one I'm going to ask you to just memorize kind of a formula for, so to speak, because it won't be quite as obvious for these functions as it was for the previous functions why it is what it is. But it'll be an easy enough formula for you to remember. Now, I want to explain the difference between the functions that we've already found horizontal asymptotes for and this, where you don't have a constant in the numerator. So let me flip back a couple of slides here to what we've done before. When we were talking about the reciprocals and translations of those, we always had a constant in the numerator. And it was impossible to divide a constant by anything that would give you 0. Alright? So it was easy enough just to say that you couldn't get 0 for your output. But now that we have a variable in the numerator and we have a variable in the denominator, it's not quite so simple as saying that we can't ever get 0 from dividing. It's still a true fact, but that's not what y can't equal necessarily here with these ax plus b over cx plus d functions. In fact, it's never that if you have a linear function in the numerator and the denominator. What we're really going to do is we're going to divide the numerator by the denominator. Now, from Algebra 2, you might remember doing polynomial division or synthetic division, those types of things. That's basically what I'm talking about. But here's what I'm going to need you to do, is just kind of accept this fact for now, and then I'll give you a couple examples that you can look at on your calculator to verify it. If you want to find the horizontal asymptote of a y equals ax plus b over cx plus d equation, the way that you're going to do that is simply by dividing the leading coefficients. If you will divide a by c, it will give you the equation or the horizontal asymptote. Let's write that, and then I'll give you those examples for you to try out on your calculator. Alright, so for instance, let's say that this was our rational function. Y equals 6x minus 3 over 2x plus 5. If you divide the leading coefficients of the numerator and denominator, you're going to find that the horizontal asymptote is y equals 3. Now go ahead and graph this function on your calculator. Remember to put the numerator in parentheses, and then put the denominator in parentheses as well. And what you ought to see is that at y equals 3, there will be kind of a boundary line all the way through that hyperbola. And you could try the same thing with this function. Y equals 9x minus 7 over 12x plus 1. And if you divide or make a ratio out of the leading coefficients for the numerator and denominator, it would give you y equals 3/4 in simplest terms. And you'll see that just below 1 on the y-axis, there will be a horizontal asymptote if you graph this function on your calculator. So that's how you find the horizontal asymptotes when you have a linear function divided by a linear function, is you simply divide the leading coefficients for those two functions by one another. Okay? Now that also works if they're both quadratics, as this was ax squared and bx squared. But the degree of the numerator and denominator have to be the same for that little trick to work, just like you learned in Algebra 2. Alright, now for the domain and the range. These are basically going to work the same way as they did with the reciprocal functions a little bit ago. We can make a relationship between the vertical asymptote and the domain, as well as between the horizontal asymptote and the range. Because there's only one domain value that or one number we can't plug in for the domain, and that's whatever the vertical asymptote is. We could say that the domain for this kind of function would be x is an element of the real numbers. It could be any real number, except it can't be the vertical asymptote, negative d over c. And similarly, it would be possible to get any output value except for that ratio of a over c. And so we can say the range is y can be any real number, it just can't be whatever a over c is. Alright, so keep those things in mind whenever you ask what the domain and range of a y equals ax plus b over cx plus d function is. Now, I'm going to ask you that question right now. Let's take a look at such a function right here. And we're going to do the same things we did with the previous example in the last video with this function. We're going to first identify the horizontal and vertical asymptotes. Then we're going to state the domain and range of the function. And then on the next slide, we'll go ahead and graph that function as well. Alright, so use what you just wrote down in your notes to be able to identify all of these things for parts A and B. You can pause the video and try that. I'll be back momentarily, whenever you unpause the video, in order to tell you what the right answer is. Alright, here you have the vertical asymptote and the horizontal asymptote. Remember, the vertical asymptote comes from setting the denominator equal to 0. And if you set 2x minus 1 equal to 0, you end up getting x is equal to 1/2. Alright, that's what we cannot plug in for x, because then we'd be dividing by 0. And then for the horizontal asymptote, we're dividing those leading coefficients, and y would equal that ratio. Then in simplest form, y equals 3 over 2. Alright, the domain and range are these. For the domain, like we said, x can be anything except for whatever the vertical asymptote is. And for the range, y can be anything except for whatever the horizontal asymptote is. With me, I hope? Good. Now let's use that information then to go ahead and make the graph of the function. Now we're going to want to make an xy table, of course, so I'm going to start there. And we'll talk about what we can and cannot plug in. Now when we start having variables in the numerator and denominator like this, it becomes a futile exercise to try to figure out what values of x are easy to plug in to make the division easy for mental math. So we're going to kind of discard that idea altogether, like we did with reciprocal functions, but all we really have to keep in mind is that x can't be 1/2. It could be anything bigger or anything less than that. And what I would like you to do is plug in 3 numbers that are bigger and 3 numbers that are smaller. Now let's take the numbers that are smaller. How about 0, -1, and -2? Those are the closest integers that are less than 1/2. And then for numbers that are bigger than 1/2, how about 1, 2, and 3? And either plug them in and do some mental math here if you like, or just plug these into your calculator. Again, making sure that you put the numerator and denominator in parentheses whenever you plug in the numbers on your calculator for this function. Go ahead and come up with these y coordinates, please. 3 significant figures is fine, by the way. Here's what I'm getting. And by the way, if I didn't write three significant figures like here or there, it means this was the exact value. So it wasn't a third significant digit to write in the first place. However, this one and this one, I did round to three significant figures. Alright, now we need to go ahead and graph the asymptotes, and then we can graph these ordered pairs and make our hyperbola. I'm going to start with the vertical asymptote. Remember that was x equals 1/2, so about right here. Yeah, I'll try to do a little better job of that. Alright, it turns out with my software, the only way for this x equals 1/2 to work out is if I made my intervals go by 1/2. So you see that I labeled this as a 1 right there. And that's actually x equals 1/2. The line kept clicking to some other points if I didn't do that. You don't have to do that certainly. And then the line y equals 3/2 is right there. And then let's go ahead and graph all those points that we just created over here, and then make our two branches where these asymptotes will be the boundaries, just the same way you've used boundaries in the previous graphs we've made. Alright, there's the first branch. Remember, don't use the x-axis for your horizontal asymptote or the y-axis for your vertical asymptote. Use the asymptotes that you actually graphed as your boundaries, and you've got that branch right there, and then I'll make the other branch. Ooh, a little thick. There's the other one that we want right there. Alright, so now you know how to graph any rational function that IB is going to expect you to be able to graph. There's a ton more that get way more complicated, and they're quite a lot of fun. Hopefully you remember those from Algebra 2. But this is it for what we're expected to do, so we're going to stop right there. Got one more video that's going to cover section 5.3. Normally don't make 3 videos per section, but we've got to look at some of the word problem type things involved with these rational functions. So take a look for that one, and hey, we'll see you guys later. Thanks for watching.